Today's lesson is on addition and subtraction of matrices. In previous sections, we have used matrices to store coefficients of equations in a linear system of equations, and then we solve those linear systems of equations using row operations. But additionally, we can also use matrices to store categorized information and perform calculations on those matrices. Specifically today, we will be working on addition and subtraction of those matrices. So our first example is at a second-hand clothing store. The inventory of shirts and pants are as follows. They have 12 gray shirts, 25 black shirts, 24 tan shirts, 54 gray pants, 31 black pants, and 14 tan pants. So we can organize this information into a table, and then I'm going to show you how to move that into a matrix. So notice I have this table where shirts and pants are my rows and the colors gray, black, and tan are my columns. So when I looked at the information for 12 gray shirts, I can take that information and put the number 12 in that column. Then I have 28 black shirts, so 28 can go in the black and the shirts. And then I have 24 tan shirts, and so I can put 24 in the tan shirts. Now I also have 54 gray pants, so back in the gray column, but in the pants row, I can put 54, 31 black pants, and 14 tan pants. So all of my data is now categorized in the table. Using the 2 rows and the 3 columns, I can move that information into a matrix, and I'm going to call this matrix A. And that's how you can store information into a matrix. Now, matrices are often named with capital letters, like above, A. A was a capital letter. Matrices are classified by size, by the number of horizontal rows, and then the vertical columns that they contain. So matrix A, the one we just worked on, is called a 2 by 3 matrix because it has 2 rows and 3 columns. So it's always going to be rows by columns. And usually we use like the X, kind of like a multiplication X, for the word by. Okay. Here's some more examples. Name the size of the following matrices. So for matrix B, I have 3 rows. So we have 3 by 1, 2, 3, 4 columns. So this is a 3 by 4 matrix. Matrix C has 2 rows, so that's 2 by, and it has 2 columns, so that's 2 by 2. Matrix D has 3 rows and only 1 column, so that's going to be a 3 by 1. And matrix E has only 1 row, but it has 4 columns, so that's going to be a 1 by 4 matrix. Now a square matrix is a matrix with the same number of rows as columns, like matrix C above. The 2 by 2 had the same number of rows and the same number of columns, so we can call that a square matrix. A row matrix, or row vector, is a matrix with only 1 row. Which one of these above has 1 row? E. E only has 1 row, and so matrix E can be named as a row matrix or a row vector. Similarly, a column matrix or column vector is a matrix with only 1 column, like matrix D from above. Notice D only had 1 column, so therefore we can call that a matrix column or a column vector. Now matrices are said to be equal if they have the same size and make sure you understand it as both, and if each pair of corresponding elements is also equal. So are the following equal or not equal? For the first example, I notice that the first matrix is a 2 by 2 matrix, and the second matrix that we're comparing it to is also a 2 by 2. But we can't say that they're equal yet until every single element is equal in each of the matrices. So looking at the first row and first column, I have a 3 in the first matrix but a 4 in the second matrix. Right there, I don't have to look any further. These two matrices are not equal. Yes, they have the same size, but not every single element is the same. Let's look at our next example. Again, we have a 2 by 2 matrix and another 2 by 2 matrix. Okay, so at least they're the same size. Let's make sure that they're also equal by making sure that every single element is the same. So we have a 3 in the first row, first column. That's the same. We have a -5 in the first row, second column. That's also the same. We have a 1/5 in the second row, first column in both matrices. And we have a 4 in the second row, second column in both matrices. Every single element is equal. Now I can say that these two matrices are truly equal. For our next examples, we have the instructions to solve for x, y, and z. So let's say these two matrices are equal. See, there's an equal sign, so we are assuming that they are equal. That means when I'm looking for the x spot, notice I have an x right here, x has to be equal to whatever the corresponding element is. So in this case, we know that x is equal to 12. Now I'm going to try to find y. Y is in the first row, first column, so I look at its corresponding elements in the other matrix. And so on this problem, y is equal to 3. And then our last one, I'm looking for z. The corresponding element for z is 4, so therefore I know that z is equal to 4. So I've solved for x, y, and z. For our next problem, we have a 2 by 1 matrix, and that says it's equal to a 3 by 1 matrix. This is already not possible. Because the two matrices are not the same size, they cannot be equal to each other. So this problem is simply not possible. You cannot solve for x, y, and z because those two matrices can't even be equal.